Welcome back, and I hope you enjoyed getting started with coding your first large language model solutions using GPT models. However, GPT models aren't the only large language models out there. There are lots of different types of language models we may want to use depending on our use case. We'll cover more on some of the other models later, but for now, let's just look at how we can start to interact with these other LLMs. Whilst GPT models can be accessed by OpenAI's API, there is another very popular way to interact with other models developed by Hugging Face. Hugging Face, named after the popular emoji, was founded in 2016 and is an open source organization that focuses on natural language processing and deep learning. They provide various tools and libraries to make it easier for researchers and developers to work with state-of-the-art NLP models, including pre-trained models and tools for training your own models. The most well-known package from Hugging Face is the Transformers library, which is widely used for working with large language models in Python. The Transformers package provides a wide range of pre-trained NLP models, including BERT, GPT-2, Roberta, and many others. It offers a simple API for loading and using pre-trained models. You can easily load a model, tokenize text, and make predictions or generate text within just a few lines of code. You can fine-tune pre-trained models on your own data for specific tasks like sentiment analysis, named entity recognition, or text classification. Hugging Face provides tools and examples to help you with this process. Hugging Face has a vibrant community of developers and researchers contributing to their projects. They offer extensive documentation and tutorials on how to get started with different projects and models. The Transformers library also seamlessly integrates with popular deep learning frameworks like PyTorch and TensorFlow, making it accessible to a wide range of developers. The Transformers package makes working with large language models simple. In our next lessons, we'll get familiar with working with the Transformers package before moving on to our larger practicals in sections 5 and 6 of this course. We can easily get started using the models available to us through the Transformers package by using the Transformers pipeline. This pipeline makes it easy for us to connect to a language model, give an input, and receive our output, all in just a few lines of code. So the first thing we want to do is import the packages. So from Transformers, import pipeline. The first example we're going to look at is a pipeline for sentiment analysis. To do this, we create our sentiment classifier. Then we can use the pipeline function. Within the pipeline function, we provide the type of pipeline we want to run. In this case, it's sentiment analysis. We can then run our sentiment classifier over a new piece of text. So let's take the phrase, "I'm so excited to be learning about large language models." We can see that just this one line of code has given us the output for the sentiment of this piece of text. It's given us the label as positive and the associated confidence score. You might also notice that when we ran the pipeline function, we were given a message that said that no model was supplied, so this pipeline has defaulted to the default model used for this pipeline. For each pipeline, there is a default model associated, but we can also specify which specific model we want to use. Let's test this out and create a new pipeline for named entity recognition. We again use the pipeline function, specify the pipeline as NER for named entity recognition, and we can select the specific model we want to use. Let's now run this pipeline over a new piece of text. We'll take the phrase, "Her name is Anna, and she works in New York City for Morgan Stanley." And we can see our output here. Our named entity recognition pipeline has correctly identified the named entities within this piece of text. The pipeline is able to abstract away a lot of the tasks for us, such as pre-processing our text input and providing an interpretable output. The Hugging Face Models Hub has information on all the different models we can use. You can search for specific models, or you can filter by specific tasks. Let's try some zero-shot classification. Remember what we mean by zero-shot learning from earlier in the course? It's where the model is able to perform a task without any additional training. The general knowledge it has learned is enough for it to complete the task. Let's see if a language model can classify some text without being explicitly trained on the classifications. We create our zero-shot classifier, we create our pipeline, and we want to use the pipeline zero-shot classification, and then we want to use the Facebook model we found on the Models Hub. If it's your first time using this specific model, the pipeline will download this model for you, but because I've used it already, we don't need to do that step. For zero-shot classification, we need our sequence that we want to classify, and we need our candidate labels. These are the labels that we're going to classify our sentence into. So we'll take the phrase, "One day I will see the world," and ask our language model to classify this as either travel, cooking, or dancing. We can then run our zero-shot classifier over our sequence to classify and the candidate labels. You can see we've been given 3 objects in our output: the sequence, the labels, and the scores for each label. Our model has identified that the phrase, "One day I will see the world," is most likely going to be about travel. So we've done no explicit extra training for this model, it's just able to use what it knows about the world to do some classifications for us. You can see just how easy it is to start working with language models using the transformer pipeline. There are lots of different pipelines we can use for different types of tasks, so do spend some time looking over the documentation for more information on the pipelines available. Using the transformer pipeline makes it quick and easy to start working with language models. Let's now do a deeper dive into what this pipeline is actually doing and try to understand the steps a little better. The first step of the pipeline is to tokenize our input text. So to do this, we want to import the auto tokenizer from the transformers package. Next, we need to specify the model we want to use. This will ensure the tokenizer tokenizes in a way that is suitable for our intended model. Different models will have slightly different ways of creating their tokenization. So we're going to be specifying our model, and we'll be using BERT base uncased. We'll cover more of this model in detail in the next section of this course. We then want to call the pre-trained tokenizer for this model. So we create our tokenizer and then use autotokenizer.fromPretrained and our model. Let's see how this tokenizer works by running it over a sentence. We'll take again the sentence, "I'm so excited to be learning about large language models." We then want to call the tokenizer on this sentence. So we'll create our input IDs and then use the tokenizer over our sentence. Let's now print out these input IDs and inspect them. We can see three things have been generated here: input IDs, token type IDs, and an attention mask. The token type IDs are used for some models where we want to distinguish one sentence from another, or an input sequence and its relative classification. We can use numbers to distinguish one sentence from another, where tokens with the type ID of 0 would belong to the first sentence, and token types with ID of 1 would be the second sentence or the classification. We'll come on to this more when we look at specific models in more detail later in this course. The attention mask essentially tells the model which words are important to pay attention to. Again, we'll cover this later in the course. For now, I just want to focus on the input IDs. The first thing our tokenizer does is break out our sentence into tokens. We can call this step directly using the following. So we want to create our tokens, and then we can use tokenizer.tokenize over our sentence. We can then print these tokens out and see that this sentence has been converted into tokens for us. These tokens are then converted into a numerical value based on a predefined vocabulary specific to the model. Let's have a look at these. We'll create our token IDs and then use tokenizer.convert tokens to IDs over our tokens. Let's then print out these token IDs. We can see that for each token, this has been converted into a numerical representation. We can decode these token IDs back into tokens to check this. So let's create some decoded IDs and use tokenizer.decode over the token IDs. When we print these decoded IDs out, you can see that we're back to our original sentence. Let's look again at the token IDs. You'll notice that the token IDs are present in the input IDs we were given when we ran the full tokenizer. However, if you look at the input IDs again, you'll see there are some additional numbers that haven't been printed when we just look at the token IDs. So, what are these? We can decode them to check their meaning. Let's run tokenizer.decode 101. This has printed out a token of CLS. Let's then run tokenizer.decode 102. And we can see we have another special token here, which is SEP. These are special tokens added by our tokenizer, and our next lesson will cover exactly what each of these special tokens mean. The tokenization process does change depending on what model we want to use, as each model has its own unique requirements for the input data in terms of its format, tokenization strategy, and use of special tokens. Let's look at how LLaMA, another large language model, differs in its tokenization. So let's specify our model as LLaMA base cased, and we'll create this as our model 2. We then create our tokenizer 2 and use auto-tokenizer.fromPretrained model 2. This will load up the tokenizer for the LLaMA base cased model. Let's now call this tokenizer on our sentence. Again, we've been given a list of input IDs, token type IDs, and an attention mask. But you can start to see some differences here. The numerical values given to each token are different, and the token type IDs now contain more than just zeros. Let's first look at how this model tokenizes differently to the BERT model above. We'll run tokenizer2.tokenize over our sentence. When we print this out, you can see that even just the way that this model has tokenized the text looks very different to what we saw above. We can then convert these tokens to their ID values. So we'll use tokenizer2.convert tokens to IDs over our tokens. And when we print this out, you can see that the numbers given to each of the tokens differs again from the BERT model above. You might also notice that where the BERT model started the input IDs with this CLS special token, XMLnet doesn't begin the input IDs with this special token at all. Instead, we see two extra numbers at the end of our input IDs. Let's decode them and see what they mean. We'll run tokenizer2.decode, and we want to decode the number 4. We can see that again we've been given the SEP special token, just in a slightly different format. And if we run tokenizer2.decode over the number 3, we can see again this CLS token, again just in a different format. But what are these special tokens, and why are they added to our input sequence? Let's move to our next lesson to discuss this in more detail. Special tokens are a fundamental concept in the world of large language models. Special tokens are specific placeholders or markers that help the model perform various tasks and handle specific tasks or instructions within the text. They are like signposts or markers that help the model understand the structure and context of the input text and guide its behavior in various tasks. This ensures the output of the tokenization is in a format that your model of choice will understand. Let's talk through some key types of special tokens and their purposes. The first are the CLS and SEP tags. The CLS tag is a classification tag, and SEP stands for separator. These special tokens are commonly used in tasks like text classification and sentence pair classification. In a typical scenario, you might have a sentence or text passage and you want the model to classify it into a category or determine its relationship with another sentence. The CLS token is usually placed at the beginning of the input, and the SEP token is used to separate different segments of text. The mask token is used in tasks related to masked language modeling or text generation with a blank to fill in. For example, you might provide a sentence with a word replaced by mask, and the model's task is to predict the missing word. This is commonly used in tasks like text completion. Depending on the specific task you want the model to perform, you may introduce custom special tokens. For instance, if you're using the model for translation, you might have a special token like source and target to indicate the source and target languages respectively. These tokens help guide the model's behavior during the translation. When you feed multiple sentences of varying lengths into the model, you may need special tokens for padding, which is where we add extra tokens to make sure all the inputs are the same length. Or we might want to use truncation, which is where we shorten longer inputs to a specific length. These tokens ensure that the inputs are consistent and align with the model's architecture. Each model will have different requirements and uses when it comes to special tokens. That's why it's important that that we specify which model we are going to use when we're working with a tokenizer, so it can ensure that it processes the text in the correct format for that model. Hugging Face makes it simple for us to work with PyTorch and TensorFlow workflows. This is useful when integrating large language models into existing machine learning solutions you may already have. And it allows us a method for fine-tuning any models. Here we will introduce how to start working with Hugging Face and PyTorch. If you'd like to work with TensorFlow, the code is very much the same. You'll just want to use the TensorFlow specific classes. Usually these are just the same class names with TF added to the name. So from transformers we want to import the pipeline, auto tokenizer, and the auto model for sequence classification. We'll also import the torch package. We already have our sentence and our input IDs from earlier, so let's print these out and refresh our memory. To get our output in the correct format for PyTorch, we need to specify we want the input embeddings to be returned as tensors. Let's update our tokenizer for this. So we'll create our tokenizer and then use autotokenizer.fromPretrained and specify the model we're going to use. This is a fine-tuned model from the Hugging Face models page that can classify text as positive or negative. We'll then create input IDs PT, and we'll use our tokenizer over our sentence, and we want to specify return tensors equals PT. This will return our input IDs as a PyTorch tensor. We can print these out to check it has worked. And yes, you can see the output is the same, but it's now formatted within a PyTorch tensor. Let's now create our model. So we'll use auto model for sequence classification, .from pre-trained, and again we'll specify our model. We're now ready to use PyTorch on our inputs to do some inference of our own. So with torch.nograd, we obtain the logits by running the model over our input IDs PT. We then want to return the label of positive or negative for our input text. So we'll get our predicted class ID, and to use this we'll take argmax.item and then we take our model.config.id to label of this predicted class ID. This is essentially looking at the dictionary mapping of the numeric scores to the classification labels. So it's looking to see whether it should return positive or negative. And once this is printed, we can see it's been returned as positive. So let's see what our sentence was. I'm so excited to be learning about large language models. So yes, a positive classification seems appropriate here. These steps are essentially what is happening under the hood when we use the pipeline function. But being able to work with PyTorch, TensorFlow, and Hugging Face together in this way means we have so many options to customize our models and understand what is happening when we use more abstract methods such as the pipeline. Let's say you've been working on a model and now you want to save it for future use so you don't have to retrain it with your data each time. Hugging Face allows us to do this easily. we first want to set our model directory where we want to save our models. So we'll create a folder called My Saved Models. We can then save our model and tokenizer by using the Save Pre-trained method. We just need to provide the model directory of where we want to save the tokenizer and where to save our model. We can then reload our models using from pre-trained. So if we want to load up the tokenizer we just saved, we can load up my tokenizer and then use autotokenizer.fromPretrained and specify the model directory where the tokenizer is saved. It's the same with our model, so we can load up my model and then use automodel for sequence classification.fromPretrained and again specifying the model directory where our model is saved.